Okay, now we need to think about drag, wind resistance. We know that if you're driving down the freeway at 110 kilometers an hour and you stick your hand out the window, the wind gives a really strong backward force on it. So if it's doing that just your hand, it must be doing a lot more to the whole car. So clearly this is pretty important at highway speeds. Even cycling, you know, wind resistance can be quite a big effect when you're cycling fast. So how can we calculate it? Well, it turns out that wind resistance can happen in two different ways. When you're moving slowly, the fluid can flow nice and steadily past an object. This is what's called laminar flow. Very smooth and steady. So this is our object. In this case you've got a wind current going this way past it, but it could be that this object is moving that way and the air is steady. That's laminar flow. But a probably more common situation is turbulence. Turbulence is when you can't draw smooth flow. So here we have our object with the wind going past it, but now the wind is doing all sorts of complicated things. It's going in circles. And these two have quite different effects, as you would imagine, on how much wind resistance there is. How do you know which is going to be the case? Well, there's a rule of thumb. There's a number called the Reynolds number. Which is a very widely used number in fluid dynamics. And what is it equal to? Reynolds number is equal to the density of the fluid times its velocity times a length scale, which is roughly speaking the size of the object. That can be a bit hard to define, but Reynolds number is not a very precise number anyway. And it's divided by mu, which is what's called the dynamic viscosity, which is a measure of the fluid friction. So this would be very low for something that flows easily like air, very high for something like syrup, and intermediate for something like water. Now rho is the density, is about, so it's 1.2 kilograms per cubic meter for air at sea level. Mu, the dynamic viscosity, is about 2 by 10 to the minus 5 Pascal seconds for air. More for water, much more for treacle. And the rule is, if R is large, say bigger than around 1,000, turbulence. Whereas if R is, say, less than about 10, laminar. This isn't very precise. There's a whole intermediate realm between 10 and 1,000 where the flow can be as a bit turbulent, a bit laminar. It'll depend on the exact shape and size. Sometimes you could be over 1,000 and still be laminar if it's a carefully designed shape and so on. But this gives you a rough figure. If R is enormous, you've probably got a turbulence. If it's pretty small, laminar, but there's a whole sort of intermediate area where it's a bit turbulent and a bit laminar and a bit more confusing. This whole confusion, of course, is what keeps fluid dynamicists and aircraft engineers and so on in work. So what's happening for a car? So let's say we have a car driving down the road. So what's the size of the car? I guess it's a cross-sectional size. Let's say it's about 2 meters tall, so L is about 2 meters. V, the velocity, 110 kilometers per hour converted to meters per second. If we then plug this into the equation, we come out with R, so V is about 30 meters per second, which is about 110 kilometers an hour. So we end up with R equals the density, which is about 1, times the velocity, which is about 30, times the length scale, which is about 2, divided by 2 by 10 to the minus 5. Which comes out as about 3 by 10 to the minus 5 goes to the top, is 10 to the 5. The 2's cancel, so it's about 3 by 10 to the 1 times 10 to the 5, so about 3 by 10 to the 6. This doesn't have units, it's a dimensionless number. The units on the top and bottom are the same. So that's enormous, 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 way more than 1,000. So that's telling us the airflow around a car is turbulent.